Welcome to Science 2 Sleep By. Tonight, as the world slowly dims and most of the United States settles into sleep, something far away is wide awake. 93 million miles from Earth, the Sun, our steady, familiar star, has developed a dark, restless scar on its surface. A massive sunspot. It looks quiet, almost peaceful, but beneath that darkness, enormous magnetic forces are twisting, tightening, and waiting. And right now, that sunspot is aimed directly at Earth. This is not a story of fear. This is a story of space weather, of invisible storms, and of how deeply connected our modern lives are to a star we rarely think about at night. So slow your breathing. Let your thoughts drift upward, beyond the atmosphere, beyond the moon, and let's gently explore why scientists are watching this sunspot so closely, and why, this time, it's not looking very good. If you like my videos, please subscribe my channel and hit the bell icon. Let's start. Sunspots are among the most fascinating and misunderstood features on the surface of the Sun, appearing as dark, irregular patches that seem almost like wounds on an otherwise glowing star. Yet they are neither holes nor signs of decay, but regions of extraordinary magnetic activity that reveal the Sun's hidden complexity. To understand why sunspots form, it helps to imagine the Sun not as a solid object, but as a vast, seething ocean of superheated plasma, where charged particles are constantly rising, falling, and circulating in slow, massive currents. Deep beneath the Sun's visible surface, powerful convection carries heat outward, much like boiling water rising in a pot, and normally, this heat escapes freely, radiating into space as light and warmth. However, in certain regions, the Sun's magnetic field becomes intensely concentrated, twisting and knotting itself into structures so strong that they interfere with this upward flow of energy. Where the magnetic field tightens, it acts like an invisible lid, suppressing convection and preventing hot plasma from reaching the surface efficiently. As a result, these areas cool slightly compared to their surroundings, dropping from roughly 10,000 degrees Fahrenheit to about 7,000. Which is still unimaginably hot by earthly standards, yet cool enough to appear darker when contrasted against the blazing solar disk. This contrast is what creates the visual appearance of a sunspot, a shadow-like feature that stands out sharply against the Sun's brilliance. Sunspots often form in pairs or groups because magnetic field lines emerge from the Sun's interior in loops, with one end carrying a positive magnetic polarity and the other a negative one, anchoring themselves to the surface like cosmic tent stakes. These paired regions can grow, merge, or fragment over time, evolving over days or weeks as the magnetic forces beneath them shift and reorganize. The size of sunspots can vary dramatically, from small patches barely larger than Earth to colossal formations that could swallow our planet several times over. And it is often the largest sunspots that draw the most attention from scientists. Because size usually correlates with magnetic complexity and stored energy, importantly, sunspots are not random blemishes. They follow an approximately 11-year solar cycle during which the Sun's magnetic field gradually flips polarity, moving from periods of relative calm to times of intense activity when sunspots become more numerous and more powerful. During solar maximum, the Sun's surface can be crowded with sunspot groups, each one a potential source of energetic events, while during solar minimum, weeks may pass without a single visible spot. What makes sunspots especially significant is not their appearance, but what they represent beneath the surface: vast reservoirs of magnetic energy under tension, slowly building as the Sun rotates and its plasma flows stretch and twist magnetic field lines ever tighter. When these fields become too stressed, they can suddenly rearrange themselves in explosive events known as solar flares, releasing immense amounts of energy in seconds, or ejecting enormous clouds of charged particles into space as coronal mass ejections. In this sense, sunspots act as warning signs, quiet indicators that the Sun is storing energy in ways that can eventually affect the entire solar system. To the naked eye, when viewed safely through proper filters, a sunspot may seem still and silent, but in reality it is the surface expression of dynamic forces operating deep within the Sun's interior. forces that dwarf anything humans can generate on Earth. Understanding sunspots has been a gradual process, stretching back centuries to early astronomers who noticed dark markings drifting across the sun and realized, for the first time, that the heavens were not perfectly unchanging. Today, spacecraft continuously monitor sunspots across multiple wavelengths, allowing scientists to map their magnetic structures and estimate their potential for activity, transforming what once appeared mysterious into something that can be studied, measured, and anticipated. And yet, despite all this knowledge, sunspots retain a quiet sense of awe, reminding us that our star is alive with motion and energy, governed by physical laws that operate on scales almost impossible to fully imagine. As you think about sunspots forming far away on the sun's surface, it can be calming to remember that these dark regions are not signs of danger by themselves, but natural expressions of a star doing what stars have always done, slowly cycling through phases of restlessness and calm, shaping the space around them in subtle, powerful ways while Earth continues its gentle journey beneath the steady glow of the night sky. The current massive sunspot now facing Earth is remarkable, not just for its size, but for the intricate and restless magnetic architecture woven through it, a structure that tells a quiet yet serious story about energy building beneath the sun's visible surface. When scientists observe a sunspot like this, they are not simply measuring how dark it appears or how wide it stretches across the solar disk, but carefully examining how its magnetic fields are arranged. Because magnetic structure is the key to understanding its potential behavior, this particular sunspot spans tens of thousands of miles, large enough to dwarf Earth itself, and it is composed of multiple dark cores, known as umbrae, surrounded by lighter, filament-like regions called penumbrae that ripple outward like frozen waves in a glowing sea of plasma. Each of these regions represents a different magnetic environment, and together they form a complex system where magnetic forces are constantly pushing, pulling, and rearranging themselves. At the heart of the sunspot, the magnetic field is exceptionally strong, thousands of times more intense than Earth's magnetic field at the surface, and it rises vertically from the sun's interior before curving outward and looping back down elsewhere on the surface. These magnetic loops act like stretched rubber bands under tension, storing enormous amounts of energy as the sun's differential rotation slowly twists them over time. The sun does not rotate as a solid body. Its equator spins faster than its poles, and this difference in speed gradually wins magnetic field lines around each other, tightening them and increasing their instability. In a sunspot of this size and complexity, those twisted fields do not remain neatly separated, but press against neighboring magnetic regions, sometimes with opposite polarities, creating boundaries where stress accumulates quietly and persistently. What makes this sunspot especially notable is its magnetic classification, which reflects how mixed and disordered its polarities have become. When positive and negative magnetic regions are closely intertwined, rather than cleanly separated, the likelihood of sudden magnetic reconnection increases. Magnetic reconnection is the process by which magnetic field lines break and rejoin in new configurations, releasing stored energy in the form of radiation and high-speed particles. In simpler sunspots, where magnetic fields are more orderly, this energy tends to remain contained. In more complex sunspots, like the one currently under observation, the magnetic landscape resembles a tightly knotted rope, where even a small disturbance can trigger a rapid and powerful release. Beneath the visible surface, the sunspot is anchored deep within the sun's convective zone, where rising and sinking currents of plasma constantly buffet the magnetic structures from below. These motions feed energy into the sunspot, preventing it from dissipating quickly and allowing it to persist for days or even weeks. As long as the magnetic field remains strong, the sunspot resists the surrounding convective flow, maintaining its dark appearance and defined shape. Over time, however, subtle changes occur. The edges of the sunspot may fray, new umbrae may emerge, and older regions may fade. All signs that the magnetic configuration is evolving in response to forces both above and below the surface. The sheer scale of this sunspot amplifies its significance. A sunspot large enough to be seen from Earth using proper solar filters is already impressive. But when one grows to a size that spans a significant fraction of the Sun's visible hemisphere, it becomes impossible for scientists to ignore. Size alone does not guarantee dangerous activity, but large sunspots almost always indicate large magnetic systems, and large magnetic systems have the capacity to produce powerful solar events. The energy stored within such a region can exceed that of billions of nuclear bombs, released not all at once, but in bursts that vary in strength and duration. From Earth's perspective, the orientation of the sunspot matters greatly. As the Sun rotates, different regions come into view, and when a complex sunspot rotates to face Earth directly, any solar flares or coronal mass ejections it produces are far more likely to intersect with our planet's orbit. This is why scientists pay close attention to sunspots during the days when they are centered on the solar disk, a position that maximizes the potential for Earth-directed activity. The current sunspot has reached this central position, meaning that if it releases a significant eruption, the resulting wave of energy and particles would have a direct path toward Earth. Observations from space-based solar observatories allow scientists to peer into the sunspot across multiple wavelengths of light, revealing details invisible to the human eye. In ultraviolet and X-ray images, the region around the sunspot glows with hot plasma trapped along magnetic loops, forming arches that rise high above the surface. These glowing loops are visual evidence of magnetic confinement and stress, and their shape and brightness can change rapidly in response to shifting magnetic conditions. When loops brighten suddenly or twist more tightly, it often signals that energy is building toward a potential release. Despite its imposing presence, the sunspot itself is not an immediate threat. It is better understood as a loaded system, one that may or may not discharge its energy in a way that affects Earth. Many large sunspots rotate across the Sun without producing major events, gradually breaking apart and fading as their magnetic fields weaken. Others, however, unleash multiple flares or powerful ejections over the course of their lifetime, particularly when their internal magnetic structures are highly stressed. Predicting which outcome will occur is one of the great challenges of space weather forecasting. Requiring continuous monitoring and sophisticated modeling, there is something quietly humbling about contemplating the structure of such a sunspot, knowing that it is the product of physical processes operating on scales far beyond human experience. The Sun, though familiar and life-giving, is also a dynamic and sometimes volatile star, constantly reshaping its magnetic environment as it burns through its fuel. Sunspots like this one serve as windows into that deeper activity, offering scientists clues about how magnetic energy is generated, stored, and released within stars. This massive sunspot continues its slow journey across the Sun's face. It does so at the unhurried pace of celestial motion, reminding us that even the most powerful forces in the solar system unfold over time. For now, it remains a region of intense interest, watched carefully but calmly, its dark form silhouetted against the Sun's glow. And as you let your thoughts settle, it can be soothing to remember that this immense structure, so vast and energetic, is still governed by natural laws that scientists understand increasingly well, allowing humanity to observe, anticipate, and adapt. Even as our star quietly reminds us of its enduring power, when a sunspot turns to face Earth, it is not the dark patch itself that causes concern, but the invisible geometry of space that suddenly lines up between our planet and the Sun's restless magnetic forces. From our perspective, the Sun rotates slowly, carrying different regions across its visible face over the course of about 2 weeks, and when an active sunspot reaches the central portion of the solar disk, it occupies a position where anything it releases has a clear, unobstructed path toward Earth. This alignment matters because solar activity does not spread evenly in all directions. Instead, energy and charged particles often erupt outward along the orientation of the Sun's magnetic field, forming directed flows rather than gentle, spherical waves. When those flows are aimed squarely at our planet, their effects are felt far more strongly than when they erupt from regions near the sun's edge and dissipate into empty space. In this Earth-facing position, the sunspot becomes a potential source of solar flares whose radiation reaches our planet in just over 8 minutes, traveling at the speed of light. These flares can increase radiation levels in Earth's upper atmosphere almost instantly, subtly altering the ionosphere, the electrically charged layer that plays a critical role in radio communication. For listeners drifting towards sleep, it may be surprising to realize that even quiet nighttime radio signals depend on the sun's behavior, bouncing off invisible atmospheric layers that respond delicately to changes in solar energy. When a strong flare occurs from an Earth-facing sunspot, those layers can thicken or thin rapidly, disrupting high-frequency radio signals across wide regions of the United States, particularly at higher latitudes. More significant, however, is the possibility of a coronal mass ejection launched from an Earth-aligned sunspot. Unlike the flash of a flare, a CME is a massive, expanding cloud of magnetized plasma that moves through space at hundreds to thousands of miles per second. Its journey is slow enough that scientists can track it, model its path, and estimate its arrival time, but its scale is difficult to fully comprehend. Such a cloud can stretch millions of miles across by the time it reaches Earth's orbit, carrying with it a magnetic field that can interact powerfully with our planet's own. When the magnetic orientation of the CME opposes Earth's magnetic field, the interaction becomes especially efficient, allowing energy to flow into near-Earth space more readily. This is why the phrase, "facing Earth," carries such weight in space weather discussions. It signals not certainty, but increased probability, a reminder that alignment enhances connection. The sun is constantly active, releasing energy in many directions, but Earth only feels the full effect when it happens to be in the line of fire. During these periods, scientists heighten their monitoring, watching not only for eruptions, but for subtle changes in the sunspot's magnetic structure that might indicate rising instability. Even small shifts can alter the likelihood of an Earth-directed event. From a broader perspective, this alignment highlights how interconnected the solar system truly is. Earth's orbit places it within a dynamic environment shaped by the sun's outflow, a continuous stream of particles known as the solar wind that fills interplanetary space. Most of the time, this wind flows gently around our planet, sculpting Earth's magnetic field into a teardrop shape that stretches far behind us, forming a long magnetic tail. When a powerful CME arrives, it compresses this magnetic bubble on the sun-facing side, pushing it closer to the planet and injecting energy into the system. This energy can then cascade through Earth's magnetosphere, setting off a chain of reactions that ultimately reach down toward the upper atmosphere. For people on the ground, these processes remain invisible, but their effects can ripple through the technologies woven into daily life. Satellites orbiting Earth pass through regions where charged particles become more intense during geomagnetic disturbances, increasing the risk of electronic interference or surface charging. GPS signals, which rely on precise timing as they pass through the ionosphere, can experience slight delays or distortions, affecting navigation accuracy for aircraft, shipping, and everyday smartphone use. Power grids, especially in regions with long transmission lines, can pick up induced electrical currents during strong geomagnetic storms, placing additional stress on transformers and infrastructure. Yet even as these possibilities exist, it is important to hold onto a sense of proportion. Earth has been facing sunspots for billions of years, long before technology entered the picture, and our planet's magnetic field has proven to be a remarkably resilient shield. Most Earth-facing sunspots pass without incident, their stored energy dissipating harmlessly into space or releasing eruptions that miss our planet entirely. The concern arises not from inevitability, but from vulnerability, from the understanding that modern society relies on systems sensitive to space weather in ways previous generations did not. There is also something quietly poetic about this alignment, about the idea that a region on the sun, slowly rotating into view, can draw the focused attention of scientists across the world. It is a reminder that Earth is not isolated, but part of a larger cosmic dance, moving in step with a star whose rhythms shape both the days we live and the nights we rest. When a sunspot faces Earth, it invites us to look outward, to acknowledge that even in the stillness of night, vast processes are unfolding beyond the atmosphere. As you let this idea settle, it can be comforting to remember that awareness itself is a form of protection. By understanding what it means for a sunspot to face Earth, scientists can prepare, operators can adjust systems, and society can absorb the impact of solar activity with far less disruption than in the past. The sun may be active, but it is also predictable in its cycles, governed by physical laws that unfold slowly and rhythmically over time. While an Earth-facing sunspot naturally draws attention and caution, it does not demand fear. It simply marks a moment of alignment, a brief window during which our star and our planet are more directly connected. And as Earth continues its steady rotation beneath the night sky, that connection becomes just another part of the quiet, ongoing story of a solar system in motion, one that has carried life safely for ages and continues to do so, even as the sun occasionally reminds us of its immense and enduring power. Solar flares and coronal mass ejections are often spoken of together, but they are distinct expressions of the sun's magnetic restlessness, each unfolding in its own way and on its own timescale. And understanding them softly can make the idea of a solar storm feel less abrupt and more like a natural rhythm of a living star. A solar flare begins deep within an active region, usually near a complex sunspot, where magnetic field lines have been twisted and stressed over time by the sun's slow rotation and turbulent plasma flows. When these magnetic lines suddenly realign through a process known as magnetic reconnection, energy that has been stored quietly for days or even weeks is released in a matter of minutes. This release manifests as an intense burst of electromagnetic radiation, spanning the spectrum from radio waves to X-rays and gamma rays, all traveling outward at the speed of light. Because this radiation moves so quickly, Earth feels the effects of a solar flare almost immediately. In just over 8 minutes, the energy arrives, subtly altering the upper atmosphere on the sunlit side of the planet. The ionosphere becomes more energized, absorbing or reflecting radio waves differently than before, which can cause brief communication disruptions, particularly for high-frequency radio users. For most people, these changes pass unnoticed, but they are reminders that even light itself, when intensified by a flare, can influence the thin layers of air far above our heads. Strong flares can also increase radiation exposure for astronauts and high-altitude flights, which is why airlines and space agencies monitor solar activity carefully. During periods of heightened activity, coronal mass ejections, on the other hand, are slower, heavier, and more physically substantial events. While a flare is a flash of energy, a CME is a vast cloud of charged particles, primarily protons and electrons, bound together by magnetic fields that erupt from the sun's outer atmosphere, or corona. These eruptions occur when magnetic loops anchored in sunspot regions become so stressed that they can no longer contain the plasma trapped within them. When they finally break open, they hurl billions of tons of material into space, forming an expanding bubble that carries part of the sun's magnetic field along for the journey. The relationship between flares and CMEs is complex. Some powerful flares occur without producing a CME, releasing energy but leaving most of the sun's plasma in place. Conversely, some CMEs are launched with only modest flares, quietly sending massive clouds into space with little immediate radiation. When both occur together, the flare can be seen as a kind of signal flare, while the CME becomes the slower-moving messenger that may interact with planets days later. This distinction is important because it is typically the CME, rather than the flare, that drives the most significant geomagnetic storms at Earth. As a CME travels through space, it moves through the background flow of the solar wind, sometimes slowing down, sometimes accelerating, depending on conditions along its path. Scientists track these clouds using spacecraft positioned between Earth and the Sun, measuring changes in particle density, speed, and magnetic orientation. The magnetic field embedded within the CME is especially critical. If it is oriented southward, opposite to Earth's northward pointing magnetic field at the day side, the two fields can connect more easily, allowing energy to transfer efficiently into Earth's magnetosphere. This interaction can trigger a cascade of effects, from shimmering auroras to disruptions in technological systems. Despite their dramatic descriptions, solar flares and CMEs are not rare or unnatural events. They are part of the sun's normal behavior, occurring more frequently during the active phase of the solar cycle and less often during quieter periods. Over billions of years, Earth has been exposed to countless solar storms, and life has persisted, evolving under the influence of this ever-changing space environment. What has changed is not the sun, but humanity's reliance on delicate technologies that extend beyond the planet's surface and into space. There is something almost meditative about imagining a CME leaving the sun, expanding slowly as it crosses the vast distance to Earth. A silent traveler moving through the darkness. Unlike sudden disasters, its arrival is anticipated, giving scientists time to prepare and respond. Power grid operators can adjust systems, satellite controllers can place spacecraft into safe modes, and astronauts can seek shelter, all guided by data flowing continuously from solar observatories. This ability to anticipate rather than react transforms solar storms from sources of fear into manageable natural events, at the same time. Solar flares remind us that the sun operates on its own schedule, releasing energy in bursts that reflect the underlying complexity of its magnetic field. These bursts are not acts of intent, but the natural outcome of physical laws playing out on a grand scale. The sun does not aim or threaten. It simply evolves, responding to the forces within it. Understanding this helps soften the language often used to describe solar activity, replacing alarm with awareness. As you think about these processes, it can be comforting to recognize how layered Earth's defenses truly are. Our atmosphere absorbs much of the sun's radiation, while the magnetic field deflects charged particles, and together they create a protective cocoon that has shielded life for eons. Even during strong solar storms, the effects at the surface are usually subtle, manifesting more in data streams and electrical measurements than in anything we can see or feel. Solar flares and coronal mass ejections, then, become part of a larger story about balance and resilience. They are expressions of energy release in a system that cannot remain perfectly still, moments when the sun adjusts and redistributes the forces within it. And as Earth continues to orbit this active star rotating gently beneath the night sky, these events serve as reminders of our place within a dynamic universe, one where immense energies can coexist with the quiet stability that allows us to rest, to observe, and to drift peacefully towards sleep. Once a solar storm leaves the sun, it begins a long and quiet journey through interplanetary space. A voyage that transforms an explosive eruption into a slow-moving cosmic tide. This journey starts when a coronal mass ejection, having broken free from the sun's corona, expands outward in all directions. Its charged particles and magnetic fields carried away from the star by their own momentum and by the ever-present flow of the solar wind. Near the sun, this cloud is dense and compact, but as it moves farther away, it spreads and thins, growing to immense proportions, while gradually losing its initial intensity. By the time it approaches Earth's orbit, the CME may spend millions of miles across, a vast, invisible structure drifting through the darkness between worlds. The speed of this journey varies widely depending on the energy of the eruption. Some solar storms race through space, reaching Earth in less than a day, while others take 2 or 3 days to arrive, moving at a more measured pace that allows scientists to follow their progress in detail. Spacecraft positioned between Earth and the sun, such as solar wind monitors, act as sentinels, continuously sampling the flow of particles and magnetic fields that pass by. These measurements help researchers estimate when the leading edge of a CME will arrive and how strong its interaction with Earth might be. There is a certain quiet patience in this process, as data accumulates slowly, hour by hour. painting a picture of a traveling disturbance that cannot be rushed or stopped. As the CME travels, it interacts with the solar wind, the constant stream of charged particles flowing outward from the sun. If the CME is faster than the surrounding wind, it can plow into this background flow, compressing material ahead of it and forming a shock wave similar to the bow wave of a ship moving through water. This shock can accelerate particles to high energies, some of which may reach Earth even before the main body of the CME arrives. If the CME is slower, it may be overtaken by faster streams of solar wind from behind, altering its shape and magnetic structure. These interactions make each solar storm unique, shaped not only by its origin on the sun, but by the dynamic environment it crosses on its way to Earth. During this journey, the magnetic field carried by the CME remains a central focus of scientific attention. This embedded field is frozen into the plasma, moving with it as a unified structure, and its orientation can change as the cloud twists and evolves. Predicting this orientation in advance is one of the most challenging aspects of space weather forecasting, because small changes can have large consequences for how the storm will interact with Earth's magnetic field. Scientists use models to simulate how the CME expands and rotates, but there is always an element of uncertainty, a reminder that space, though governed by physical laws, remains a complex and dynamic system. As Earth comes closer to the path of the traveling storm, the planet's magnetic field begins to feel its influence. Long before the CME arrives, subtle changes may occur in the solar wind, signaling that the environment around Earth is shifting. When the leading edge of the storm finally reaches our planet, it first encounters the magnetosphere, compressing it on the sunward side and stretching it on the night side. This compression can cause sudden changes in magnetic measurements, a clear sign that Earth is now interacting with something larger than the usual solar wind. When scientists say they are concerned, but not panicking, it reflects a careful balance between respect for the sun's power and confidence in human understanding, a balance that has been refined over decades of studying space weather and learning how our star behaves. Concern arises from observation, the size of the sunspot, the complexity of its magnetic fields, and its direct alignment with Earth, all increase the probability of significant solar activity. These factors are measurable, repeatable, and grounded in well-tested physics, giving researchers real reasons to pay close attention. At the same time, panic has no place in scientific thinking, because the sun operates within known patterns, and even its most dramatic outbursts follow laws that can be observed, modeled, and anticipated with increasing accuracy. Space weather scientists have learned that solar activity exists on a spectrum, not as a simple choice between calm and catastrophe. Most solar flares and coronal mass ejections, even from large and complex sunspots, produce only modest effects at Earth, many of which pass unnoticed outside of scientific instruments. The concern surrounding the current sunspot is not that disaster is inevitable, but that conditions are favorable for stronger events than average. This distinction is important, especially in a world where headlines can amplify uncertainty and turn careful scientific language into alarm. In reality, scientists work in probabilities, weighing multiple factors to estimate risk while acknowledging that nature always retains some unpredictability. Modern monitoring systems form the backbone of this calm confidence. A fleet of spacecraft constantly observes the sun, tracking changes in its surface, atmosphere, and magnetic field across a wide range of wavelengths. These observations allow scientists to detect early signs of instability, such as rapid changes in magnetic structure or the sudden brightening of plasma near active regions. When an eruption occurs, additional instruments monitor the solar wind and the interplanetary magnetic field, providing real-time data as disturbances travel toward Earth. This layered awareness transforms solar storms from sudden surprises into anticipated events, allowing time for preparation rather than reaction. This preparedness extends beyond scientific observation into practical response. Power grid operators in the United States receive alerts when geomagnetic activity is expected to increase, giving them the opportunity to adjust loads and protect critical equipment. satellite operators can place spacecraft into safer configurations, reducing the risk of damage from increased radiation. Airlines can alter flight paths at high latitudes to minimize communication disruptions and radiation exposure. These measures do not eliminate all risk, but they significantly reduce the likelihood of widespread disruption, turning potential crises into manageable challenges. The phrase, "not looking good," often reflects the complexity of a situation rather than an expectation of harm. A large, magnetically tangled sunspot facing Earth is, by its nature, something to watch closely, much like a powerful storm system forming far out at sea. Meteorologists do not panic when they see a hurricane develop. They observe, model, and inform, allowing communities to prepare calmly and effectively. Space weather forecasting follows the same philosophy, grounded in the understanding that awareness is the most effective form of protection. There is also an important historical perspective that tempers concern with reassurance. Earth has endured countless solar storms over billions of years, including events far more powerful than most of what we observe today. Even the strongest recorded geomagnetic storms did not threaten the planet itself, only the technologies that happened to exist at the time. While modern society is more technologically interconnected, it is also far more knowledgeable, with systems designed to anticipate and withstand environmental stress. This combination of vulnerability and preparedness defines our current relationship with space weather. A relationship built on respect rather than fear. Inside the magnetosphere, energy from the storm is redistributed along magnetic field lines, flowing toward the polar regions where the field connects most directly with the atmosphere. This energy transfer can set charged particles into motion, guiding them downward toward the upper atmosphere, where they collide with atoms of oxygen and nitrogen. These collisions produce the shimmering curtains of light known as auroras, which may spread to lower latitudes during strong storms, becoming visible far beyond their usual Arctic home. For observers on the ground, these lights can feel like a quiet gift from a distant storm, a visual reminder of processes unfolding far above the clouds. At the same time, the energy injected into Earth's magnetic environment can induce electrical currents both in space and on the ground. In space, satellites may experience increased radiation, affecting electronics and sensors. On Earth, long conductors such as power lines can pick up geomagnetically induced currents, adding stress to electrical infrastructure. These effects unfold gradually, often over many hours, rather than in a single dramatic moment, allowing operators to respond and adapt as conditions evolve. Throughout this entire journey, from the Sun to Earth, the solar storm remains invisible to human senses. There is no sound, no vibration, no sudden change in the night sky, only a subtle rearrangement of magnetic and electric fields that quietly influences the space around our planet. This invisibility can make solar storms feel abstract or distant, but in reality, they are as much a part of Earth's environment as the weather patterns that move through the atmosphere below. There is something soothing about considering this slow passage through space. A reminder that even the most energetic events in the solar system often unfold over days rather than seconds. The storm does not rush. It drifts, guided by forces that have shaped the solar system for billions of years. Earth, in turn, responds not with fragility, but with resilience, absorbing and redistributing energy through systems that have evolved to handle such encounters. As you imagine this journey continuing through the dark, it can be comforting to remember that solar storms are not invaders, but travelers, moving along paths set by the sun's activity and the structure of space itself. Their arrival is anticipated, their effects measured, and their departure inevitable. And as the storm eventually passes, the solar wind returns to its usual gentle flow. The magnetosphere relaxes, and Earth resumes its quiet balance, carrying with it the memory of yet another interaction between a planet and its star. Unfolding softly in the vastness of space, Earth's magnetic shield is one of the planet's most quietly powerful features, an invisible structure that surrounds the world and protects it from the constant stream of energy flowing outward from the sun. This shield, known as the magnetosphere, is generated deep within Earth's interior. where molten iron slowly circulates in the outer core, creating electric currents that in turn produce a global magnetic field. From the surface, this field is subtle, guiding compass needles and shaping auroras. But far above the atmosphere, it expands into a vast protective bubble that deflects most charged particles before they can reach the planet. Under calm solar conditions, this magnetic shield functions smoothly, gently steering the solar wind around Earth and maintaining a stable environment in near-Earth space. However, the magnetosphere is not rigid or unchanging. It is flexible, responsive, and sensitive to conditions in the surrounding space. When a strong solar storm approaches, particularly one carrying a powerful magnetic field of its own, the balance between Earth's field and the incoming energy can be disrupted. The sun-facing side of the magnetosphere becomes compressed, pushed closer to the planet, while the night side stretches far into space, forming a long magnetic tail. This reshaping happens gradually, often over hours, as Earth adjusts to the changing pressure of the solar wind. Much like a boat rocking gently as waves pass beneath it, the orientation of the storm's magnetic field plays a crucial role in determining how much energy enters Earth's system. When the magnetic field carried by a coronal mass ejection is aligned opposite Earth's own field, the two can connect through a process called magnetic reconnection. This connection opens a pathway for energy to flow directly into the magnetosphere, increasing its internal activity. In these moments, Earth's magnetic shield does not fail, but it does work harder, absorbing and redistributing energy throughout its structure. This process is natural and has occurred countless times over the planet's history, shaping space weather patterns without ever completely overwhelming the system. As energy enters the magnetosphere, it is guided along magnetic field lines toward the polar regions, where those lines dip down into the upper atmosphere. There, charged particles spiral downward, colliding with atoms of oxygen and nitrogen at altitudes far above the surface. These collisions produce the soft, glowing lights of the aurora, transforming invisible magnetic interactions into visible motion across the sky. During stronger storms, this auroral oval expands, allowing people at lower latitudes to glimpse the lights, a gentle reminder of the dynamic forces at play beyond the atmosphere. While auroras are the most beautiful expression of geomagnetic activity, other effects unfold more quietly. Within the magnetosphere, electric currents intensify, flowing through regions of space that are normally calm. Some of these currents connect to Earth's upper atmosphere and, indirectly, to the surface. Long conductive structures, such as power transmission lines, can experience small but significant induced currents during strong geomagnetic disturbances. These currents do not originate within the power grid itself, but are driven by changes in Earth's magnetic field, a subtle coupling between space and ground that reveals how deeply interconnected our planet has become with its cosmic environment. Satellites orbiting Earth also feel the strain when the magnetic shield is disturbed. Increased particle radiation can affect onboard electronics, cause temporary malfunctions, or degrade solar panels over time. Changes in the upper atmosphere during geomagnetic storms can increase atmospheric drag on low Earth orbit satellites, altering their paths slightly and requiring careful adjustments to maintain stable orbits. These effects are monitored closely, allowing satellite operators to respond with protective measures, such as powering down sensitive systems during periods of heightened activity. Despite these vulnerabilities, it is important to recognize the remarkable resilience of Earth's magnetic shield. Even during the most intense solar storms recorded, the magnetosphere has absorbed and redistributed energy without collapsing. The largest known geomagnetic storm, the Carrington event of 1859, produced spectacular auroras and disrupted early telegraph systems. But Earth itself emerged and changed, continuing its orbit as it always has. Today, technology is more sensitive, but our understanding is also far greater, allowing us to anticipate and mitigate many of the risks associated with severe space weather. As you think about Earth wrapped in this magnetic cocoon, it can feel calming to imagine the planet drifting through space, shielded by forces born deep within its core. Solar storms may come and go, pressing against this barrier, but the response is measured and controlled, governed by physical laws that have proven reliable over immense spans of time. The magnetosphere is not a wall, but a living structure, responding dynamically to its environment while maintaining its essential protective role. So, when scientists speak of Earth's magnetic shield struggling, they do not mean that it is failing, only that it is being tested, momentarily pushed as it absorbs a surge of energy from the sun. These moments of strain are part of a long-standing relationship between Earth and its star, a relationship marked by balance rather than conflict. And as night deepens and the world grows quiet, it can be comforting to remember that even in the face of powerful solar forces, Earth remains well guarded, cradled within an invisible shield that continues to do its quiet work, allowing life below to rest, dream, and endure. And now, as this story gently draws to a close, you can let go of the tension that words like massive and not looking good sometimes carry. The reality is calmer, steadier, and far more measured. Earth continues to turn beneath its magnetic shield. The atmosphere continues to hold us. Technology continues to adapt. The sun continues to shine, as it always has, sometimes quietly, sometimes with bursts of energy that remind us of its living nature. So take a slow breath and imagine the planet drifting peacefully through space, watched over by scientists, protected by invisible forces, and guided by laws that have endured for billions of years. The sun may stir, and the skies may glow, but the night remains safe, the ground remains steady, and rest is still possible. Let the vastness of space soften into stillness, and allow yourself to drift into sleep, carried by the quiet assurance that even when the cosmos seems restless, balance, understanding, and calm remain firmly in place. Good night.